Good evening, ladies and gentlemen, and welcome to the Vernon Lecture Series, sponsored by Mount Cuba Astronomical Observatory and the Astronomical Foundation, and joint with the University of Delaware. And our special guest speaker tonight is Dr. Joseph Taylor. And as part of the introduction, I want to give you a little background on Joe. So before I introduce him, I first met Dr. Taylor during my undergraduate years at Stockton State College. I studied under his late brother, Hal Taylor. And I stopped by Hal's house one night late to drop off some papers I graded. His wife answered the door and said that Hal was back in the radio closet. And that's what I found out it literally was. It was the pantry. And Hal had all his radio equipment stacked up. And he was talking to his brother, Joe. The antenna, I think Hal must have climbed 30, 40 feet up in that tree to strap the antenna. And I think, if I'm not mistaken, Joe, I think you were at Arecibo at the time. This was the late 70s. So I was watching these two guys communicate via ham radio, and I got inspired for a minute to become a ham radio operator. And then I thought, I'm not climbing that tree 30, 40 feet, so that was the end of that. Went back to optical. But there's another story I'd like to tell you. Joe and his brother Hal grew up on a farm in Siddaminson on the banks of the Delaware River. And that's where they developed their interest in astronomy and ham radio. And there's a story that goes that these two boys would salvage parts from discarded television sets. And for those who would remember, those were radio tubes back in those days, not the solid state. Well, these upcoming scientists decided to design a bigger antenna for their interest in ham radio. And similar to optical astronomers, we want bigger mirrors. Radio astronomers want bigger dishes. Well, these two boys, they wanted a bigger antenna. So there's one little problem when they designed this antenna. It sheared off the chimney of the 1720s farmhouse that they grew up in. So Joe, I'm not going to ask, but I'm just going to assume that your father made you and Hal muck quite a few stalls on the farm that day. So for those of you who are into ham radios, I'd like to introduce to you K1JT. And everyone else who came out tonight to hear about Einstein's theory of gravity and black holes and relativity, I'd like to introduce you to Dr. Joseph Taylor, the 1993 Nobel Laureate and Professor Emeritus at Princeton University. Joe?
Thanks very much, and good evening, everyone. I'm going to take off my jacket. It's a little warm, and we've got work to do. So it's a great pleasure to be with you, and my plan is to tell you a story this evening, and it's a story that extends over a little bit, just a few years more than a century. It's partly science, very current science, in fact, having to do with gravitational waves, which are among the hot topics at the frontiers of physics today. But it starts 100 years earlier when Einstein formulated his generalized theory of relativity, which is currently our very best theory of gravitation. And it's so if you like, there's some science here, but there's also some history of science. And another way of describing what I have to convey to you is a case study of the scientific method in action, because that's really what this amounts to, and one that extended over a long period following a tortuous path that was not straight at all. It had many side paths and blind alleys sometimes, and I want to focus on a few of those that are of particular interest. So just to get some of the dates more or less focused in your mind, Einstein in 1905 published, he was 26 years old at the time, 25 or 26, I guess he turned 26 during that year, and he published 5 important papers, astonishing papers, probably any one of which was a plausible candidate for a Nobel Prize. One of those was about the special version of relativity, one that deals with electromagnetic phenomena and other things that have to do with velocities that may approach the speed of light, but which do not involve gravitation or accelerations. So it's a sort of a limited theory of relativity. It was 10 years later, he realized, of course, that this was not the whole story, and that history has taught us over the years, going all the way back to the days of Newton, or if you like, even farther than that, it's useful to look for, when we're trying to understand nature's laws, to look for ways in which they can be unified, that we can get theories that describe a larger range of phenomena, probably closer to the true way that nature operates. At any rate, in 1905, Einstein certainly recognized that the special theory of relativity was not capable of accounting for gravitational phenomena, and he turned much of his attention to solving that, sort of filling in that gap. Well, that took him another decade. It was not until 1915 that he published the general theory of relativity, which doesn't treat accelerations and gravitational phenomena. Well, I'll have a lot more to say about that, but let me just go through the rest of these nutshell descriptions of things that happened at various different times. The general theory of relativity made specific predictions, one of which was that rays of light should be bent slightly when they pass by strong gravitational fields. That means, among other things, that there was an explicit prediction that if one could make adequate photographs of the stars close to the sun during a solar eclipse, when the moon is covering up most of the sun's light, that we should be able to see the stars displaced by a small amount from their normal positions. And by measuring that small bending of light, one could establish whether this particular prediction of the general theory of relativity was correct. Now, another prediction of the relativity theory, the general theory, was that gravitational radiation should exist, gravitational waves that should propagate through space-time, carrying energy with them in rather the same way that electromagnetic waves, including radio waves, microwaves, infrared, optical light that you can see with your eyes, ultraviolet, all this whole spectrum of electromagnetic radiation is different spectral slices of the same phenomenon. But gravitational waves are an entirely separate thing, and they don't involve electromagnetism, they involve the force of gravity. So people were discussing and, in fact, arguing about whether these gravitational waves really exist, and if so, could they possibly be detected? And that took place over a long time. I focus here on the years from sort of 1920 to 1960-ish, in the middle of which, of course, came the Second War, at a time when science more or less had to shut down and this kind of thing, this kind of exploration. But in any case, those were important years for establishing some of the exact ways in which the general theory would make predictions about a kind of radiation which had never then been observed, and perhaps would lead to ways of making experimental tests to see if, in fact, nature behaves the way this theory said it should. That's part of the scientific method, after all. You come up with a description of a lot of phenomena that can be embodied with mathematical rigor into a theory, and then you use it to make predictions and establish whether, experimentally, whether those predictions turn out to work. In the 1960s, there was a phenomenon, a discovery of the phenomenon known as pulsars, which turns out to be important in this description, and I'll tell you a few things about those. A particular type of pulsar, one that was orbiting around another star and therefore was a member of a binary system, a so-called binary pulsar. That turned out to be an extremely important discovery, and that's the one that led to my own honor in the Swedish Academy with the Nobel Prize, and I'll tell you some things about that experiment. There were still some theoretical controversies about whether we really understood exactly what Einstein's theory would predict under a given set of circumstances. And one of these controversies centered around an equation first derived by Einstein that's been called the quadrupole formula. It's a simplified way of calculating how much energy should be radiated in the form of gravitational waves under a given set of conditions. And we didn't know until the 1980s for sure whether that formula, which is an approximation as derived by Einstein, actually would give the correct answer in a more rigorously defined way. And finally, there's the discovery of gravitational waves by the so-called Laser Interferometer Gravitational Wave Observatory, LIGO, which we'll get to, and which sort of closes out the century of this history that I want to be telling you about. So this tortuous path, it turns out, involves not one, not two, but 4 Nobel Prizes, and I'll highlight each of those as we go. The first of which was the Nobel Prize to Einstein in 1921. It wasn't actually given by the Swedish Academy for the relativity theory, but for one of those other papers in 1905, but it could just as well have been the relativity papers. In any case, by that time, he was an established and famous man, particularly so because of the experimental confirmation of the bending of starlight during a solar eclipse, which I'll say a few words about in a minute. Then the discovery of pulsars itself turned out to be an important astrophysical discovery that was awarded a Nobel Prize in 1974. My own work in 1974, which led to experimental observations over 20 years and longer, led to a Nobel Prize in 1993. And finally, the discovery of gravitational waves by LIGO, the direct detection of those waves, led to the Nobel Prize in 2017. So I'll say a few words about each of those events. So let's go back to the beginning. Here's Albert Einstein at age 26, working as a patent clerk in the Swiss Patent Office because he couldn't find a good academic job at the time. But he published these 5 fantastic papers during that year. Here he is a few years later, hard at work on general relativity theory. He hasn't quite got there yet, but he will soon. And in 1915, the general theory is published. So one of the predictions in 1915 was that starlight should bend when it passes by a massive object. The massive object, in effect, distorts the space-time in its vicinity, and the light follows the path that's the straightest path in some sense in that curved space-time. I won't try to identify or define those terms any further, but suffice it to say that starlight or any other type of light, any other type of electromagnetic radiation will follow a path that gets slightly distorted by a large gravitational field. The amount by which the bending occurs is vastly smaller than this exaggerated picture. In fact, it's a tiny fraction of 1 degree, but it's a calculable number within relativity, and it's something that you could, in principle, go and look for. And here are the actual solar eclipse observations made by the British astronomer Arthur S. Eddington during a solar eclipse in 1919. This picture is exactly the photograph that was published in the paper in which he presented their results. It's a negative, so things that are light here are dark on the sky. So there's the white circle in the middle is the sun covered up by the moon, so it's dark. The black stuff around it is the solar corona, so that's actually light, but it's the outer atmospheres of the sun. And what you can't see really very easily, unless you're maybe close to the front of the room, are the little tick marks that I've circled a few of here, which identify the particular stars that Eddington and his collaborator focused themselves on to see whether they had been displaced slightly from their normal positions by the presence of the sun. 6 months later, the sun isn't here anymore, but those same stars could be photographed again and you find where they are normally, and then in this photograph you tell where they are when the massive body, the sun, is in that position. And in fact, they were found to be displaced by just about the amount that was predicted by Einstein's theory. I say just about because this, in fact, is a difficult experiment, and with the equipment available at that time, it was not done with very high precision. They got the right answer, but with an uncertainty of 30% or so. So it was basically hailed as a success of the prediction. It made Einstein famous overnight. There were headlines in newspapers around the world, like this one in the Times in New York, saying, "Lights all askew in the heavens, men of science more or less agog over the results of eclipse observations," et cetera, et cetera. Basically, this was an experimental confirmation of what had seemed up to that time to be a rather esoteric, not very practical theory, or a theory without much in the way of practical consequences. However, in science, we follow nature's laws wherever they lead us, and if this really was correct, we had to take it seriously. So it led to, well, I mean, it and other contributions made by Einstein, of course, led to his attention to the award committee at the Swedish Academy, and he was awarded the Nobel Prize in 1921. We'll come back to those things again, or at least to other instances. So let's focus for a second on this notion of gravitational wave-like solutions to Einstein's theory. Important questions arise. The equations that mathematically define what this theory has to say about the universe involve, I mean, they have wave-like solutions. So you can see that the waves appear to be mathematically admissible in this theory. But important questions that would have been asked at the time involve some of these that I've written down here. Are the solutions, mathematical solutions, physically meaningful? Are we sure that the waves are independent of the chosen coordinate system? The mathematics of these equations is not straightforward, it's not simple, and you have to adopt a coordinate system in which to do calculations. It wasn't at all clear that the waves would survive transformation from one type of coordinates to another, for example. Was it necessarily the case that these waves are a consequence of general relativity? Could they somehow be a mathematical artifact without much more significance than that? If they are real, could we calculate their speed, the energy that they carry? Things like that would certainly be important. And if they're real, those things must be, in the end, something that we should, in principle, hope to understand. And finally, we might ask the question, could such waves possibly be detected at some distance away from whatever was generating the waves? That, of course, had been done for radio waves, electromagnetic waves, only a quarter of a century before this time, and led to the rise of not only radio and television, but lots of other things that we take for granted today, to say nothing of streetcars and elevators and everything else that works with electric motors. So anyway, it was important to know where this understanding would lead us. So here are some quotations taken from various different papers written in the 1920s, having to do with the question, do gravitational waves really exist in general relativity? That is, this is not an experimental question or an observational question. This is a theoretical question. Does this theory really require that gravitational waves should exist? And the answers are all over the place. There are no gravitational waves. Plain gravitational waves traveling along the x-axis can be found. Gravitational waves do not exist. Do gravitational waves exist? It turns out that rigorous solutions exist. And interestingly, all these were written by Einstein himself. He was not at all sure at this point exactly what the basic field equations were telling us, and nobody else was sure either. Maybe you've heard the quip that a reporter once asked Arthur Eddington, said to him, "I've heard that there are only 3 people in the world who understand Einstein's theory." And Eddington paused for a while, and the reporter said, "Well, don't be modest, tell us a little bit more about it, and who understands it?" And Eddington said, "I can't think who the 3rd person is." Anyway, So this was the question at the time. Do these waves really exist according to the theory? Einstein's own papers, the 1915 publication of the theory itself made it seem as though the equations allowed wave-like solutions. He made some explicit calculations in 1916 that involved this thing we call the quadrupole formula. He actually made a mistake in the calculation at that point. The answer that he got was off by a factor of 2, but basically that was the correct explanation as we understand it now. And a couple of years later, he did it more thoroughly and corrected the factor of 2 error. So the 1918 paper is the one that's frequently quoted to be the sort of first complete prediction that gravitational waves should exist and should carry a calculatable amount of energy with them. But still, there were still people that were not convinced. There were others who made calculations as well. Eddington was one of those, and one of the problems with relativity is that it's a so-called nonlinear theory. If gravitation is present, that increases the energy, and that in turn increases the gravitational field so that it feeds on itself, and that makes the calculations difficult. Anyway, Eddington used a so-called linearized approach, which means that he got a set of results that were correct only in a very weak gravitational field. But it turns out that that was actually a pretty good way to begin, because anywhere in the solar system, for example, on the Earth or anywhere, say, orbiting in the solar system, the gravitational fields are, as far as relativity is concerned, weak fields. So good way to start. So Eddington, and on the basis of that weak field approximation, reached the conclusion that yes, gravitational waves must exist in this theory. But Einstein and another collaborator, Nathan Rosen, in 1936 submitted a paper that I'll tell you more about in a minute because it's fascinating, in which their conclusion was originally no, that these gravitational waves don't exist, that they show up in the equations, but only in a way that is mathematically an oddity, but will go away when you can make them go away by considering different coordinate systems. It turns out that that paper, as most physics papers these days, and those days too, at least in this country, are submitted to anonymous referees before they are published. And it turns out in this case, in 1936, the anonymous referee said the paper is wrong and here's why it's wrong, and their answer should have been yes, when in fact their answer had been no. Anyway, I'm going to tell you some more about that story in a minute. Turns out the referee was right and Einstein was wrong, which is kind of interesting. We'll get to that. And in the end, after the referee's report was returned to Einstein, they came up with the sort of hedge, maybe. Anyway, this story, by the way, if you're fascinated by these kinds of things, you should read it in the original. It's a book called, written by Daniel Kennefick at the University of Arkansas. The name of the book is Traveling at the Speed of Thought. We in physics often talk about the speed of light. It turns out Eddington once talked about, I mean, when people were arguing about gravitational waves existing, one of the arguments against them was that the waves would make themselves felt at some distant point immediately, rather than having to propagate there, as though they had traveled at the speed of thought, which is even faster than the speed of light. Anyway, it's a good title for a book. It was published by Princeton University Press about 12 years ago. So here's a letter, as quoted by Kennefick in his book, a letter written by by Einstein to his friend and scientist in Germany, Max Born. By the way, as I'm sure you know, Einstein left Germany and left Europe more or less permanently as the Nazis rose in Germany. He came to this country in 1932, and so at this point he's in Princeton at the Institute for Advanced Study, but writing back to his friend in Germany. He says, together with a young collaborator, that's Nathan Rosen, I arrived at the interesting result that gravitational waves do not exist. though they had been assumed a certainty to the first approximation. So he and Rosen write their paper. They send it off to the Physical Review, probably the most prestigious physics journal in this country. The title of the paper was, "Do Gravitational Waves Exist?" And the answer given in the paper was no. Now, Einstein didn't know it because he, up to that time, had published his papers in European journals, primarily, entirely European journals, primarily German ones, I guess. And the tradition there was that if you were an established scientist, whatever that means in the mind of the editors of the journal, your paper just was published. It wasn't reviewed formally. But that wasn't the case in the Physical Review. John Tate, who was then the young editor of the Physical Review, wanted to make it into the best physics journal in the world, and he was adamant about having all papers, before accepting them for publication, reviewed by some other expert in the field to see if there were any problems. So the Einstein and Rosen paper is sent to a referee. And I'm just realizing I've forgotten the piece of paper that I was going to have with me, so I'm going to have to tell you what was in it. Anyway, Tate writes back to Einstein, and his letter includes this sentence, that we would be glad to have your reaction to the various comments and criticisms the referee has made. Okay, seems like, at least to those of us today who are accustomed to this kind of reviewing of scientific literature, a perfectly reasonable thing to do. Here's the letter that Einstein wrote back 4 days later, and obviously you can't read it, but it's handwritten, kind of scratchy, and basically it says, Herr Rosen und ich, Herr Rosen and I, thank you for the report. We sent you our paper for publication, not for criticism. And if this is your attitude, we prefer to withdraw the paper and publish it elsewhere. So that's basically, I've translated the German for you. I don't think I've conveyed the high dudgeon in which it was written very well, but anyway, and by the way, Einstein never sent a paper again to the Physical Review. He published elsewhere after that. Well, okay, here I even have the translation, even though I didn't do it for you. Mr. Rosen and I had sent you our paper for publication and had not authorized you to show it to specialists. I see no reason to address the, in any case, erroneous comments of your anonymous expert. On the basis of this incident, I prefer to publish the paper elsewhere. Okay, so this, by the way, is a translation done by Diana Buchwald, who is the principal editor of the Einstein Papers Project, a project now run out of an office at Caltech. The Einstein papers are being published serially by Princeton University Press. They're up to, I think it's volume 16 now, and there are going to be about 30 volumes. So much of this stuff can actually be found in the published versions of the early 16 volumes of the Einstein papers. Well, it turns out this man, Howard Robertson, was the referee to whom Tate had sent the paper for review. And this is the one that I'm sorry to say I don't think I have here the translation or the words from, so I'm going to have to tell you what was in it. But he writes back to the editor, John Tate. He says, "Dear Tate," that's the way you address people in the 1930s, I think, scientific colleagues. "Dear Tate, well, this is a job. I'm happy to review the paper of your most famous contributor." And he goes on to say, it's all very interesting, but, and then he has a list of 14 points. There were a couple of minor typographical problems that were easy to fix, but there was a fundamental problem in the paper, and Robertson recognized it and explained exactly what the problem was. And apparently, although when Tate sent the thing back to Einstein, he sent Robertson's report anonymously, so Einstein didn't know that he was being critiqued by a man who was also in Princeton, just in the Princeton mathematics department, not at the Institute for Advanced Study, but they knew each other. Anyway, it turns out I don't think Einstein had read or attempted to really understand Robertson's critique. He just didn't like being critiqued at all, and wasn't going to give it a second thought. What happens then? Well, although I said Robertson was in the math department at Princeton, he actually, when he did this refereeing job for Tate, he was at Caltech. On leave for the semester, so he did this at a distance. The next semester, he was back in Princeton again, and he made it a point to go have lunch with Einstein one afternoon and explained to him. I don't think he ever came clean and told him, I reviewed your paper, but he did say, I've read your paper, and well, what about equation 14? You got this wrong. And anyway, he convinced Einstein that it was wrong. And here's Einstein in 1937, probably trying to think about whether Robertson was right or not, and he was. So it turns out the paper was actually published eventually in the Journal of the Franklin Institute, not a very noted physics journal, but a respectable place. And a note was that the paper's conclusions were changed, and then there was a note added in the proof galleys at the end of the paper, in which Einstein says, the second part of the paper was considerably altered by me after the departure of Mr. Rosen for Russia. Rosen had gone off to do some other things in Russia. Since we had originally interpreted our formula results erroneously, I wish to thank my colleague, Professor Robertson, for his friendly assistance in the clarification of the original error. All right, so, science proceeds this way. We make mistakes and we get them corrected, and that's part of the reason peer review is so important. When you're blazing a new trail, you can't check your answers by looking up the problem in the back of the book or something. You have to do your best job, and we hope we usually get it right, but sometimes we don't. And sometimes our colleagues can help us correct those errors. Well, I'm going to skip ahead now. This was in the late 30s. Pretty soon, the war. It was almost starting by that time already in Europe, and here a few years later. So now we're skipping into the 50s after the war. Science can start up again. And it turns out these four gentlemen are all important to the next little stage, about which I'm not going to say a great deal, but just a little bit. Richard Feynman is a man you've surely heard of, and perhaps you've read some of his books. Some of them are funny and well worth reading in any case. Herman Bondi, Ivor Robinson, Felix Pirani, all distinguished physicists, and one of the things they did was they got together. I think all four of them were present at a conference about relativistic gravitation held in Chapel Hill, North Carolina in 1957. And in particular, Feynman and Bondi at that conference made a very important contribution in which they described a so-called thought experiment, an experiment that you can do without actually being in a laboratory at all or doing anything other than thinking it through carefully from beginning to end. And their so-called sticky bead experiment, which involved a rod of some kind, perhaps a metal rod, with beads on, 2 beads on it, so that they could slide, but they had a bit of friction with the rod. And you imagine a gravitational wave coming along and calculate what should happen to the rod and the beads when the wave goes by. And you can do that from Einstein's field equations. And what should happen is the beads should move, be deflected a bit by the gravitational wave. And yes, the rod also should be expanded or contracted a bit as the gravitational wave goes by. But the beads will move farther than the rod does, and then the rod expands, because the beads are not constrained by anything attaching them, whereas the rod, after all, is solid and therefore has atomic forces between the electric charges in the atoms that makes it solid. So that resists the stretching or compression of the rod. Anyway, so the beads will slide on the rod. There's friction, and that friction will generate heat. Where did the heat come from? It's energy. It had to come from the gravitational wave. So with that thought experiment, you can be very certain that if these waves really exist, they must carry energy with them. If they exist the way gravitational theory, relativity theory says they do, then they must carry energy. Soon after that, Bondi and those other two gentlemen, Felix Pirani and Ivor Robertson, published a series of papers. Here's paper 3 in their series, titled Gravitational Waves and General Relativity, in which they lay it all out in a great deal more mathematical precision and rigor than was possible in the 1920s, say, done by Eddington with his linearized approximation. So at this point, we weren't sure whether gravitational waves exist in nature, but we were sure that Einstein's gravitation theory predicts that they exist. And not only that, we know some of their characteristics according to the theory. So if we can find the waves and actually measure them, that would be a test of the theory itself. Again, following the basic way you do these things, following the scientific method. So, new topic. I want to say a few things about pulsars at this point. Pulsars are neutron stars, that is, stars made of nuclear matter rather than ordinary atomic matter. Nuclear matter consists, at least in the way it was described in the 1950s, say, protons, neutrons, electrons, those were the particles. We know some more details about what's inside those now, but at the time, let's let it go at that. The discovery of the neutron experimentally happened in the early 1930s. Chadwick in the UK, credited with that discovery. And within a couple of years, a couple of astronomers, Fritz Zwicky and Walter Baade, wrote a short paper in which they conclude that so-called supernova explosions are the transition of a star into a neutron star. They write, this is a quote from their paper, "With all reserve, we advance the view that a supernova represents the transition of an ordinary star into a new form of star, the neutron star, the end point of stellar evolution. Such a star may possess very small radius and extremely high density." Not too long after that, 1939, J. Robert Oppenheimer, the one who contributed so essentially to the Manhattan Project during the war, and his student Robert Volkoff published a paper in which they basically derived the structure that a neutron star would have to have. It was not until a few decades later, after the war and into the 60s, before actual detection of astronomical objects which could be neutron stars first happened. The first one I remember was during my years as a graduate student, because in 1962, Riccardo Giacconi, in fact, I should have highlighted that as another Nobel Prize, shouldn't I? That's 5 for this evening. Giacconi was awarded the Nobel Prize some years later for a lot of work, but some of the first work that he did that drew attention to him was done in the early 1960s when he discovered an object which turned out to be a neutron star. Well, pulsars were discovered at the end of the 60s, or nearer the end of the 60s, in 1967. These objects are strongly magnetized, rapidly spinning neutron stars. If you spin a magnet, you make an electrical generator. So these objects basically generate strong electromagnetic fields above their magnetic poles, and as they spin, they emit a beam of radiation that swings around the sky, sort of like the water out of a lawn sprinkler or the light out of a lighthouse, a rotating lighthouse. And those give rise to periodic pulses of broadband radio noise that can be detected across interstellar distances. It turns out they're accurate clocks, if you like. That is, the spacing between these pulses, which is controlled simply by the rotation of the object, is such that the fractional change or measurement uncertainty divided by the period is 1 over 10 million or so. It's very precise. In fact, this was what was known almost right away, but within a few years we knew that it was way better than that. It was maybe 1 part in 10 to the 15 or so. And by even the end of the following year, there were already 23 pulsars discovered. I was involved in discovering quite a number of those, and so got involved in this from, as it happened, I turned in my own PhD thesis in January of 1968, just a few weeks after the discovery paper was published, and I was looking for something to do on the postdoctoral fellowship that I had been awarded, so I was basically ready to try something new, and got involved with this right from the beginning. So these are the remnants of supernova explosions. Large, high-mass stars becoming unstable because they have exhausted the nuclear fuel in their cores. They explode, leaving behind a cloud of gas expanding outward and a very dense remnant in the center, which is the neutron star. And that discovery led to a Nobel Prize in 1974 for the discovery of pulsars. So let's say a few more words about these objects. The Crab Nebula is a supernova explosion. That's a pretty astronomical object that you can see, probably in the public nights at the Mount Cuba Observatory from time to time. They point the telescope at the Crab Nebula so you can look at it. It might not look quite as beautiful as you see it here, but it's still a pretty special object. And it happens that one of these objects right near the center, see these two stars very close together? One of those is a neutron star, and it's magnetized and it spins rapidly and it generates these broadband pulses of radio noise which sweep around the sky. And there are lots of other of these objects. There are a few thousand pulsars now known, discovered since this time. The magnetic fields are extraordinarily strong. The magnetic field of the Earth is typically around 1 Gauss in these units. Here we're talking about things that are 1 billion to 1 trillion times larger. Something a bit more massive than the sun, but compressed into a sphere with a radius of only 10 kilometers or so. A teaspoonful of this material on Earth would weigh about 1 billion tons. Pretty dense. The reason, of course, is we're talking about nuclear matter. Ordinary atomic matter has a nucleus and a cloud of electrons and mostly empty space. If gravitational forces are so strong as to compress the cloud of electrons into the nuclei, basically neutralizing the electric charges of the protons, you end up with mostly neutrons, a so-called neutron star. So let's see, pulsar, just a little bit of pulsar history. The discovery in the late 60s, there were many pulsar surveys, searches of the sky using radio telescopes to find more of these objects. They were so unexpected that they were fascinating for many reasons. I got involved in work at the University of Massachusetts where we put together a scheme for detecting these objects with, of all things, a computer. We used then what was called a mini computer. It was about the size of a refrigerator and it weighed 800 pounds. But we could program it to do what we needed to do to detect these impulsive periodic signals. We put the whole machine into a big plywood crate and air freighted it down to Puerto Rico because we wanted to use our detection system with the largest radio telescope in the world, the big 1,000-foot diameter spherical dish at the Arecibo Astronomy Center. So here's the Arecibo dish. It's not quite the way it looked in 1972 when we started this project, but it's more or less what it looks like today, or maybe I think this is probably taken around the late 1990s. But as you can see, there's a fixed mirror in the ground. That doesn't move. Up in the air, 400 feet above the center of the dish, as a suspended cable work with the focus antennas that pick up the radio waves. And those can move. And I think the next few slides probably show them in a little bit more detail. The antennas inside this radome and this big antenna over here move along this sort of banana-shaped curved member, and the whole thing rotates around a central pivot in here. So you can steer the antenna by moving those things around on the focus arm, you can steer it to within any degree, any angle of about 20 degrees from straight up. So it doesn't give you full sky coverage, but it gives you a fair bit of coverage, particularly things that go overhead more or less at the latitude of Puerto Rico. If you're a movie buff and like James Bond, you may remember the movie where James Bond chases the bad guy down along this, this catwalk and down on here, and I think the bad guy ends up falling off the antenna. So, good movie. All right. Here we are in 1974 with our project to discover a lot of new pulsars. At this time, there were a couple of dozen pulsars known. We thought we had a scheme that would allow us to at least double the number of known pulsars, maybe more than that. This is our mini computer. And it's still in its plywood crate, you'll notice. All we did was take the front off the crate and stand it up. But this is Russell Hulse, my graduate student at the time, who shared the Nobel Prize 19 years later with me. He's keying the bootstrap loader into his computer, and you can see we had the old style magnetic tape drives and so forth. By late in 1974, he'd been there for a little over a year with some observing time on and off, and we had found by that time 40 new pulsars. But the most important one by far turned out to be this binary pulsar orbiting around another star. And how did we know it was orbiting? Because the period, remember, is very accurate and very precise, except that this one kept changing, and it changed in a way that repeated every 7 3/4 hours through this cycle. So this is the 7 3/4 hours repetition. This is the original graph that we published in the paper describing this discovery in 1975. And you can see the velocity varies a lot. We're measuring Doppler shifts, so we measure a velocity along the line of sight. And notice the units here, the velocity, the radial velocity along the line of sight in kilometers per second gets as big as something like 300. The speed of light is only 300,000 kilometers per second. This is 1/10 of 1% of the speed of light that this thing is moving. It is a relativistic object. It is moving far faster than any objects in the solar system move, and therefore it was pretty obvious to us at the beginning that this system could be a useful relativity laboratory where we could explore some details of Einstein's gravitation theory that had not previously been subject to experimental tests or verification. So just a few points about this object. Its period of rotation, the spin period, was 59 milliseconds. That means it spins about 16 times per second. Pretty fast. The orbital period, the period of the binary system, that's the thing just under 8 hours. The eccentricity of the orbit is quite high. It's not a circular orbit. It's a highly elongated elliptical orbit. How do we know? Well, basically because this curve is not a sine wave. It's got a sharp spike in it. And that means that during the time when the velocity is largest is when the two stars are close together, but at other times they're farther apart. It's an elliptical orbit. Okay, we could tell that the unseen companion, the other object about which it is orbiting, had to be small. Probably another neutron star, because basically another star like the sun wouldn't fit in the orbit. They would be touching. No room for that. And we didn't see any eclipses. The pulsar didn't disappear when it went around the backside of whatever it was orbiting around. So it's probably another neutron star, we thought. The effects that appear in the dynamic equations that describe its orbit that appear proportional to the speed over the speed of light squared, those are usually not important in ordinary Newtonian physics, but in relativistic physics they could be important, and because the speed is so high, those might be important, and we said they will be easily measurable. We could tell that the orientation of the elongated orbit should be rotating gradually with time. In fact, the so-called point of periastron, that's the closest approach between the two stars, should be moving around at the rate of about 4 degrees per year. So even after a year or so, we should be able to see that the orbit is rotating, and that turned out to be the case. And we estimated that we should be able to detect gravitational waves carrying energy away from the system if we keep on keeping track of the pulse timing over a period of some years. And at first we estimated it's probably going to take us 5 years or so to be able to measure that, and with precision might take us longer than that. So here's basically what we were setting out to do. We have at some distance, maybe 20,000 light years or so from the Earth. That's in our galaxy, but not in our part of the galaxy. It's sort of halfway across our galaxy, down one spiral arm, are a pair of objects. They're moving in elliptical orbits around each other. The size of the orbit is roughly equal to the size of the sun. Let's say 1 million kilometers, just to give a round number. And it should be radiating gravitational waves which carry energy away. And the energy loss should be at the rate such that the orbit shrinks by about 1 millimeter per orbit. Are you kidding me? Can you tell if this orbit, which is about 1 million kilometers, shrinks by 1 millimeter and you can tell? Yeah, we can. Over time, we can't tell it over one orbit or a few orbits, but over time it accumulates gradually, and it accumulates in proportion to the square of the amount of time you have established the data over. So it's an experiment that inherently rewards patience. The longer you wait, the bigger the effect is, and that's why we got started in doing it. Now, before I get back to the experimental result, at this point, this is now in the late 1970s, the question arises whether we really know what the theory predicts. Is this so-called quadrupole formula correct? The problem here was that the mathematical derivation from the original field equations is not, that was available at that time, certainly the one that leads to the quadrupole formula, is not mathematically rigorous. It's okay in a physics department maybe, but it wouldn't be okay in a math department. You can't quite prove the theorem that says that you can get from here to here. It takes some judgments about the way nature operates, which are not mathematically precise judgments. Now, Feynman, in that meeting in Chapel Hill in 1957, basically laid out the problem and said, here we have a situation in which we have an elegant theory, but we don't have any experiments. And at that point, in the year 1957, he went on to say, and we're not going to get any experiments. I guess he could have said in the foreseeable future, but whatever. He said we're not going to have experiments. So what should you do if you want to know what the result is going to be? Should you wait until you can actually, with mathematical precision, be absolutely certain and prove the theorems that show how you get to a particular result of a calculation? He argued, well, that's one approach, but you may not get very far that way. And he pointed out that people say sometimes that relativity is difficult because it's mathematically difficult. And he says, I don't think that's true. Lots of other areas of physics, I can't do the mathematics either. But I can get useful results by making approximations and calculating and continuing, and then maybe, hopefully sometime, getting to a point where experiment can help to show whether the calculations are on the right track or not. So he recommended strongly going ahead even if we are not yet able to claim full mathematical rigor. Shortly thereafter, a couple of his colleagues at Caltech, Peters and Matthews, published a paper in which, dealing specifically with the calculation that we used to tell us how much the binary pulsar orbit should be shrinking. And the Peters and Matthews paper begins by saying, the question has been raised whether the energy calculated the way we're going to do it has any physical meaning. We shall not concern ourselves with this question here. He just said, we're going to calculate it anyway, take it as you will. We'll find out eventually whether it's right or not, maybe. Anyway, at this time, and up until about the late 1970s, when we had discovered this pulsar and we said we were going to do this measurement to see if it was, if the orbit was decaying as gravitational radiation says it should, but we hadn't got to that point yet. And there was a lot of debate still underway, particularly among theorists interested in doing these calculations. So here are the beginning of our observations. Here's 1975. We're going to the right in time, and the vertical scale here is measuring the amount by which the orbit appears to have speeded up. And a little bit, maybe. It's starting to get a little shorter. But you can see the flags on each one of these measurements. Each dot is a measurement, and the flags on them indicate the range of uncertainty that we estimate to be associated with those measurements. So at this point, near the end of 1978, we were saying, hey, it looks like it's beginning to speed up a little bit. And in fact, it's doing so at about the rate relativity says it should. A lot of people perked up their ears and were interested in this, but they were also a bit skeptical, reasonably, because our uncertainties were still fairly large. But with time, they got better, and the fact that this effect is growing in proportion to the square of the elapsed time is in our favor, of course. So it's getting bigger, and we're getting better at doing the measurements, so the error flags start getting smaller. Here's an expanded view of the same thing. Notice that the error flags over here are getting substantially smaller than they were over there because we were optimizing the way we were using the telescope, and we were building new equipment and new software to analyze the data. So by 1982 or so, we were pretty sure we were seeing this decay at about the right rate. And at this point, particularly the theory people who were interested in this problem realized that it's really time to do this right. Let's put some significant effort into doing this derivation with full mathematical rigor. And several authors approached this problem in using different ways and different approaches. Some of the most successful were a good friend of mine, the French physicist Thibaut Damour. Another one is Jim Anderson at the Stevens Institute of Technology up in northern New Jersey. Anyway, they and others came up with results that showed now rigorously that the quadrupole formula in fact gives the correct result, that our calculations were valid, and that they were perfectly applicable to binary star systems like the binary pulsar. So we were delighted with that, and of course we kept on doing the measurements, and the results continued to get better and better. Notice now that the pulsar is reaching its point of periastron, the closest approach to the other star, about 8 seconds earlier than it would have if the period had remained constant at the value it had back in 1974 at the first discovery. 8 seconds is a big difference now compared to the uncertainty in measuring these points. And we continued making measurements, and the numbers keep getting bigger and bigger. So by something like 1993, the measurements were very reliable. We could say with about 1% accuracy, the uncertainty was about 1% of the measurement, that this was definitely showing that gravitational waves, as predicted by general relativity, exist, and they're carrying energy away from this system at the rate that relativity says they should. And that, of course, led to another great honor that I had the honor of accepting together with Russell Hulse, the student who worked with me at the time we did the work. So that's another one of these things, and I want to start another new topic. And we're going to get back to gravitational waves themselves. So we showed that gravitational waves exist, that they behave the way relativity says they should, but we didn't detect the gravitational waves themselves. We detected radio waves, which showed what was happening at the place where the gravitational waves were being emitted. We didn't detect those gravitational waves having propagated over 25,000 light years of interstellar space. Now, around the late 1960s, a man named Joseph Weber at the University of Maryland was already seriously at work on a laboratory experiment that he hoped might enable him to detect gravitational waves. And Joe Weber was clearly a pioneer in his field. He was an excellent experimental physicist. He did a lot of hard work, and he believed that he had detected gravitational waves. Unfortunately, people who tried to duplicate his experiment, to repeat it, were unable to find what he thought he had found. And in fact, we're quite sure now that what he detected was not gravitational waves, but various other kinds of disturbances to his system. But nevertheless, he paved the way toward other work that was taking place at comparable times, and which eventually led to the building of this major instrument called LIGO. I highlight here one piece of ordinary public news in the New York Times Science Times paper on Tuesday, February 27th in 1990, where they talk about the fact that the U.S. National Science Foundation has said it is going to fund the project that became known as LIGO. This was big money. The National Science Foundation was going out pretty far on a limb because it wasn't even certain at that time in many people's minds that what they were hoping to detect actually exists experimentally and can be detected. Our experiment calmed those fears a lot, and I think it was basically the fact that they thought, and as mentioned in this article, that they might be able to detect the collisions of binary neutron star systems where the two stars spiraled in so close to each other that they collide. At that point, the system would generate a huge amount of gravitational radiation, and those would be detectable over intergalactic distances by an instrument of the kind that became LIGO. And I think it was the fact that we had shown that these waves necessarily have to exist in our best existing theory of relativistic gravity that gave the U.S. National Science Foundation confidence that it was worthwhile funding this project, even though it arguably had fairly high risk. So this slide you've already seen on the teaser at the beginning. Here we see a couple of orbiting objects, presumably very dense, generating gravitational waves. The LIGO detector actually has two basic sites on the Earth now, one in Livingston, Louisiana, and one in Hanford, Washington. Each one of them, as you'll see, has two long arms, a central laboratory, and then two long arms. The arms are pipes about 1 meter in diameter, a little more, which are evacuated, a very high vacuum. They're 4 kilometers long, and they allow laser beams to travel back and forth along the arms. There are mirrors at the end and in the laboratory, and the whole system is engineered in such a way that it can measure the fact that the two suspended mirrors, the one at the end of the arm and the one in the laboratory in the center, on both of these arms will be caused to move a little bit by a passing gravitational waves, just the way that the beads on the rod move a little bit as the wave goes by. And if we can measure that motion, we can measure the characteristics of the gravitational wave. How much is a typical expected gravitational wave going to move these mirrors? It turns out the answer is something like 1/10,000th of the size of an atomic nucleus. It's even more preposterous to imagine that that's possible than our millimeter of orbital shrinkage. But these guys are clever, and they've done it, and it works. High-power lasers interfering with an interferometer, and the whole system actually works. You may remember, it was just a couple of years ago now, February 2016, big headlines, gravitational waves detected just about 100 years after Einstein's prediction. LIGO opens a new window on the universe with observation of gravitational waves. These are colliding black holes that they found. They didn't get the collision of two neutron stars. They got something even better, the collision of two black holes, some things more massive than neutron stars. So they have, for the first time, observed ripples in the fabric of space-time itself, those ripples called gravitational waves. So here's an interesting graph, and it's got some animation in a minute and some sound associated with it. So I want to tell you first what it is. So horizontally is time. over just about half a second. This is 0.5, this is 1.0, this is half a second of time. Vertically is frequency, and they're going to show here the actual motion of the mirrors converted into a sound and then analyzed for the spectrum in the sound. They can convert it basically to a voltage, which could be, if you connect it to an audio amplifier and a speaker, it could be made into a sound. The voltage itself is the important thing, and that has frequency components that range from a few tens of cycles per second up to maybe a few hundred cycles per second. These are audible. These are in an audible frequency range. So here's the Now, so you saw two sweeps. This is the horizontal sweeping is real time. That really is a half a second. The sound that you heard, first there were a couple of low-pitched, audible, sort of woofing sounds where you could barely hear this because the frequencies they're in the audible range, but at the very low end of the audible range. And the second pair of sweeps had that sound just translated up into a higher frequency so that your ears can detect it better. And let's just go back and play it again. So the sweep is this rapidly increasing frequency at the end. Whoop, whoop. Now, underneath the spectrogram is the actual waveform itself, oscillations that, as you can see, get stronger in voltage, stronger in amplitude, and higher in frequency, that is closer together. And those are exactly the characteristics that you should expect from the gravitational waves of two very massive objects when they collide. And here again are in a little bit more detail so it's easier to see, are the measurements made first at Hanford, Washington, then at Livingston, Louisiana. They're overlaid here so you can see they both saw the same signal. It was about 7 milliseconds later at Washington than it was at Louisiana. Or maybe I have that backwards, I've forgotten which one was first. But the time difference was sufficient to tell them basically which direction in the sky these signals came from. Anyway, a fantastic discovery. It was a big deal. They could actually analyze those curves in some detail and tell that the two objects that collided had to be black holes with masses of around 30 times the mass of the sun. One a little more than 30, one just a hair less. Notice that 29 plus 36 is 65, but the final object they could show had a mass of only 62 solar masses. So 3 solar masses somehow disappeared. 3 solar masses worth of gravitational wave energy was radiated away from this system. That's a huge amount of energy. It's more energy than for a short time. It didn't last very long, but for a very short time, that's more energy than all the stars and all the visible galaxies would radiate during that same time. Gravitational waves are weak in the sense that it's very hard to detect them, but they can still carry a lot of energy away from a massive collision like this. They could also calculate the distance, and turned out this thing is about 1 billion light years away. Fascinating. Here is, are the principles involved with the LIGO experiment and the ones who were awarded the Nobel Prize. Kip Thorne, Ray Weiss, Barry Barish. Here's Thorne and Weiss again. And a fourth major contributor to the project, Ron, why am I blanking on his name? Oh, I'm sorry. But anyway, sadly, he died a year before the Nobel Prize was awarded, but just after. He was suffering from dementia in his late years, but he was told about the success of the experiment and apparently knew that it had succeeded, even though he did not survive long enough to attend the Nobel Prize ceremony. Anyway, that's the last one of these I'm going to show you. And what else? The LIGO collaboration has now been joined by a European group with another instrument very similar to LIGO called Virgo. It's in the Italian Alps. It's a French-Italian collaboration. And together now, the whole collaboration has detected 10 of these mergers of black hole pairs. They've measured the component sizes of the black holes that have coalesced into one. They range all the way from 8 to about 50 solar masses. This was a surprise to astronomers that there were as many of these objects with masses substantially greater than 10 solar masses, say, than we had expected. So already it has told us significant things about the early phases, probably, of stellar evolution back when the universe was much younger than it is today. They have observed one binary neutron star merger, the endpoint of a system very like the binary pulsar. And in that case, not only were gravitational waves observed, but also light and radio waves and other forms of electromagnetic radiation. Remember, a black hole doesn't let out anything like light. They all get swallowed up. But these things can spit out some light as well and do so. And so a great deal astrophysically was learned from this system as well. The third observing run, the so-called O3, observing run number 3 for the LIGO-Virgo collaboration, started just 3 weeks ago, April 1st. And they have alternated observing runs with engineering times. During the engineering times, they've made adjustments that have improved successively the sensitivity of the instruments, so that each time they start a new observing run, they have a better system than they had the last time. And this time already within less than 2 weeks after the start, they, I think, probably detected another of these coalescence events because they issued a so-called public alert. That is, an alert sent out by email to all the astronomical observatories which might have a hope of pointing their telescope, whatever kind of telescope it is, optical or radio or infrared or whatever, to the direction where the apparent gravitational wave was detected. That's going to be a big improvement, because if you can observe other kinds of radiation associated with the gravitational waves, there's a lot more that can be sorted out from the data than you could get from the gravitational waves alone. We don't know yet what happened on April 11th, at least none of us who are not in the in-group that gets these emails. We don't know what they found, but we'll find out probably within 6 months or so. Here are just a few of the other spectrograms showing these kinds of chirps that were similar to the one you listened to, and the waveforms associated with them. They're detecting these things fairly regularly now, and they'll be even more regular with observing run 3 because their sensitivities are more than twice as good as they were before. And finally, I'll just end with this slide, which is one that you probably saw in the newspaper only, what, two or 3 weeks ago, showing the rim of a black hole taken by a so-called Event Horizon Telescope. I'm not going to talk any more about this, but it's a fascinating way to end, and to remind you that this whole area of physics, extreme gravitational physics, is a hot topic in the field these days. So I thank you very much for your attention, and I'd be happy to answer a few questions. And I think I was told that there was a microphone. Is there? Okay, we do have a microphone, and if you stick up your hand if you've got a question, we'll bring you a microphone. Okay, back here.
I don't know if you can go back to the slide that showed the 2 facilities, the LIGO facilities.
Yeah, okay.
And pardon my ignorance, but they look solid to me. How are they looking up at the sky? Yeah, but we're...
This one, you're thinking of these?
Yes.
Yeah, so a gravitational wave can't be focused and collected by a telescope the way electromagnetic waves can. Because why? Because gravitational waves go through everything. In fact, these instruments are just as sensitive to gravitational waves that arrive from below your feet down through the Earth on the other side as they are to waves that arrive from the sky. The Earth doesn't even slow these things down or attenuate them. And for that reason also, these gravitational waves can travel across the universe with no attenuation. They go right through stars, dust clouds, galaxies. Those things don't matter. They may be deflected a little bit by the passing gravitational wave, but virtually the whole wave propagates across the whole universe with virtually no attenuation. So these things don't need to be pointed in any direction. They basically simply have suspended mirrors at the ends of these tubes, and they're trying to measure the separation between the two mirrors by using laser light and interferometry. And the mirrors are only going to move a tiny amount, less than the nucleus of an atom by a lot. But the waves of the laser beam interfere in a slightly different way, in a way that you can extract. And for any one of these facilities, say the one in Louisiana, if it detected a wave, it could say, yeah, this looks like the waveform of a gravitational wave, but it would have no way of saying from what direction it arrived. That's why it was important to have two of them, because the two of them together will give a time difference, and that allows you to at least begin to localize the system. If you have three, that's even better by a lot. It will be better still when there are a fourth one or a fifth one. There's one going to be built in India, across on the other side of the Earth, jointly funded by the Indian government and the U.S. National Science Foundation. That will make a huge improvement. That'll probably come online in 2023 or thereabouts. So additional location facilities will be possible at that time. But that's a good question. Thank you for asking it. Other question? There's one right down in the front here. He's going to bring you a microphone. Then the other people can hear what you say. Here he comes.
What does a gravitational wave consist of?
We'll get to that one in a minute, because I could hear that. Well, all right, you're getting the microphone.
What does a gravitational wave consist of?
Yeah, well, what does an electromagnetic wave consist of? A radio wave. You can't see it, you can't feel it, you can't touch it, but it conveys from one place to another, from one place to many other places. It conveys really the reactions of space to the motions of electrically charged particles. That's for the electromagnetic wave. So, you have a radio antenna, a transmitter that drives electrons up and down the antenna. That generates electrical fields which propagate through space. That's the radio wave. The gravitational wave is more or less the same kind of thing, but it's gravitational forces that are involved rather than electromagnetic forces. If you make a massive object accelerate, perhaps back and forth, something like driving the electrons up and down the antenna, that will mean gravitational fields which change a little bit because of the location of the object, and those effects propagate through space at the speed of light, carrying energy and other information with them. And in the same way for gravitational forces that radio waves do for electromagnetic forces. Other than that, I'm not sure what to say. If you ask what does a gravitational wave consist of, it basically is a local distortion of space-time such that another gravitational object, in principle, would feel that distortion as the wave propagates past. And it's a little bit what that diagram of this one is supposed to be conveying. These two objects are massive stars or black holes or something going around each other, and an object over here which is influenced by gravitational forces will feel the difference in their positions as they rotate in such a way that they correspond to waves being propagated out from the center. And that's probably the best explanation I can give you. Another question here. Yep, please.
When these events are detected, Can the source, can the direction and the distance, can they be localized? And if so, do they all come from a preferred direction, or are these like totally isotropic?
Yeah, it turns out the distance can be calculated pretty well, to the nearest 1,000 light years or something. But these are a billion light years away. You can get it to 10% or so pretty accurately. Location in the sky is, now that we have 3 good detectors, is pretty good. And so we can localize them to within a few degrees. That was why it was successful to follow up the coalescence of this pair of neutron stars by other telescopes, optical telescopes and so forth. They could find roughly the right space in the sky and look for something happening there, and sure enough, they found something going on there. So that was important. The reason you can compute the distance more or less directly is because of the fact, as I described a minute ago, these waves are not attenuated as they travel through space. So basically, you can tell by how strong the wave is, and you can tell by the shape of the oscillating curve what the masses were before and after the collision, and you can tell by the amplitude of the curve how far away it must have been. And that's basically what you need to do. One more question here, and then perhaps one farther back. If you shout, I'll repeat the question.
I have a question over here.
Yeah, ordinarily, if you think of the strength of electromagnetic waves, we think they decrease in power as the square of the distance. That's true also of gravitational waves for the same reason. They spread out over time, and so over space, and so as they get farther away, they cover a larger spherical area, and that sphere grows as the square of the distance. However, it turns out that with gravitational waves, the sensitivity that we can use actually depends only on the first power of the distance rather than the second power. And the reason is because these waves are coherent. We actually measure the amplitude of the waves in, if you like, in engineering terms, it's in voltage rather than in power. Power is the square of a voltage. So with gravitational waves, we're measuring the amplitude itself, and that amplitude only falls off as the first power of distance. The power does, in fact, fall off as the square of distance, but we're not detecting power. The coherence of the wave means we can detect the wave itself. Okay, I think there was one farther back. Yeah, over here. Go ahead.
So, what can you say about mathematical significance? How the mathematics help in those discoveries?
The mathematical significance?
Yes.
Well, I think I would just say the significance is basically a significance in physics and basically understanding the laws of nature. But to the best of our understanding, nature follows laws which we can codify in mathematical equations. And what we have established here is that the mathematics which codifies Einstein's theory of relativity is consistent with the physics experiment that we have now done to detect these waves after they have propagated over a huge distance. So in that sense, we have confirmed not only the physics, but the mathematics. If you like, the mathematics is the reduction of the physics to a form that you can write down in the terms of an equation and do calculations with. It does not further mathematics as a discipline of its own, because the importance of that kind of mathematics is the internal logic of the mathematics itself. A physics experiment doesn't say anything about that, but it does say something important about the way nature itself appears to follow laws that are consistent with the way we write and use and argue with mathematical precision. Nature also is a mathematician. Okay, anyone else? Yeah, okay, over here.
I have a question about the public alerts on the LIGO system. You mentioned there was a 7-millisecond delay between the two locations. What would the timescale be until we would detect things from radio or optical or?
Oh, good question. In the one case where the radio and optical and other kinds of electromagnetic waves were also detected, that was the pair of neutron stars colliding. The delay between the gravitational wave and the other stuff that was observed varied all the way from a few seconds to a few weeks. Why is that? Well, gamma rays, for example, were observed within a small fraction of a minute, a few seconds of time. Gamma rays are very high energy electromagnetic radiation. That got out right away with the collision itself, basically. Some stuff that didn't fall into the final black hole was instead ejected outward. It was emitting gamma rays. Those were energetic enough to reach the Earth, and they reached it almost as fast as the gravitational waves. It almost necessarily confirms that gravitational waves and electromagnetic waves travel at the same speed, the speed of light. Why did the other stuff take longer? The radio waves were emitted by clouds of gas, also ejected from the explosion, but you couldn't observe them until that cloud of gas expanded large enough to generate enough power to observe. When it was compressed into a small region just around the eventual black hole, there wasn't enough power coming out. We had to wait till it got bigger. Part of the power depends on how big the radiating object is. So that took longer. And other things were somewhere in between that. So it was a fascinating range of different information coming from different wavelength regions, all of which turned out to give interesting and important additional clues as to what was happening. Okay, all the way in the back.
In the same way that there's been theories of using solar wind to propel objects through not only the solar system, but out of the solar system.
Yeah.
Has there been any talk of these gravitational waves possibly being used in that way for sending something out through the galaxy?
Well, if there has been any talk, I haven't heard it, and I would venture the opinion that any such talk is coming from a kook. Basically, gravitational waves couple so weakly to any matter that the chances of being able to extract enough energy from them to make a spaceship move, I think, are basically zero. That's not going to happen.
Question that I have for you is the illustration that you're showing obviously is two neutron stars illustrated, and I'm wondering that would seem to be rather rare, but maybe the combination and more common might be one star, but also is it possible that you would have 3 or 4, and would that change the gravitational waves?
Yeah. Binary star systems are very common in astronomy. There are a lot of binary pairs. Triple systems are rare. And when you do have a triple system, almost always, almost without exception, and for good, solid mathematical reasons, if you have a triple system, it almost certainly is a pair close together, and then a third one much farther apart than either of those two, which basically orbits around that as if it was only one. That works. And there are other multi-star systems, basically star clusters, where they all sort of orbit around each other, or like they move around like bees buzzing in a swarm with no particular repeatable orbits. That's common enough. But binary pairs are very common, and they can be stable for a long time. And that's why basically we have systems like this. Turns out pairs of neutron stars, I mentioned that there are a couple thousand pulsars known now, somewhere between 2,000 and 3,000. Of those, about 10% are in binary systems. So not that many, but a few hundred such systems are known. So they're reasonably common. I think we should probably wind this up, but how about one more question from here?
Is
Yes.
that an artifact of
Well, it's so the question was, I mentioned that the waves are coherent, and does that depend upon LIGO, I guess is what you're asking, or what does it depend upon? I think the answer basically is that when you, the kinds of radiation that we're most commonly familiar with, the various different kinds of electromagnetic radiation, for example, are, in order to be of significant amplitude, significant magnitude, they have to be generated by many huge numbers of moving charges, moving electrons. An electron itself oscillating generates electromagnetic waves, but not in detectable levels. To get a detectable level, you need 10 to the 20 of them or more, huge numbers. That's not true for the gravitational wave. And when you do get lots of electrons generating, say, the light coming out of a star like the sun, that is caused by a lot of electrons moving in random ways in the high temperature gases and so forth. Those generate electromagnetic waves, but those are incoherent because there are so many of them moving in arbitrary directions that their oscillations don't all add up at the same time. Incoherent radiation. Gravitational waves are, when you've got a couple of really massive objects, like a couple of 30 solar mass black holes, those are just a couple of objects, and they move in a coherent way and generate coherent waves. And you don't need billions of them or billions of them in order to generate enough radiation to detect it halfway across the universe. So it's a very different kind of phenomenon, and that's why its radiation detectability only goes down as the first power of the distance rather than the second power. It's that coherence that makes the difference. Thank you all very much for coming this evening. It was a pleasure talking with you.